Okay, yeah. So hello everyone. So sorry for the slight delay. I was facing some issues while joining Teams from my laptop, but yeah, I hope they are resolved now. So hello everyone. I think since this is the first time we are meeting, so just let me introduce myself. So I'm Lakshya Saggi, the problem solving TA for social network analysis NPTEL course. So this will be my first time also. I'll be TAing social network analysis. I've TA'd for NPTEL in the previous semesters, but mostly for algorithms and discrete maths courses. So this will be my first time. So yeah, please excuse me if I mess up in if I slip up in first two lectures or something, because yeah, this is the first time I'm handling this course. So just to maybe get started okay, I think there's a question in chat. Okay, so Zaki is saying that so Zaki is saying that this is your first time in NPTEL course and you're enrolled as part of Swayam. Can I just briefly go through how the Swayam portal actually works? Okay, so Zaki, maybe I'll just share my screen and tell you how to access this course. So maybe I'll just share my screen first. Share screen. Yeah. Okay. So first of all, you have to. So I hope my screen is visible right now. So, so first of all, Zaki, first when you go to this swayam.gov.in, so there is this Swayam portal at which you have to start out with the course. So here, when you so I'm already logged in, but you will have to first log in and yeah. As soon as you log in into the course, so there will be in your profile there because my courses, my certificate, sign out. So you just go to my courses, and you can see the course in which you are registered. So upcoming course, this is the social network analysis course in which you are registered, and now you can go to course. So when you go to course, here is this so most of the course announcements will be posted on this forum. So this forum will act as official announcement forum for you guys, and here you can find in this week one, you can find these lectures. So these are week one's lectures, and similarly there will be a quiz at end of every week. I believe you need to pass these quizzes for if you have taken the certification, for if you want a certification for this course, and there will be a exam at the end also if you want to be certified. So yeah, so these are every week's quizzes and these are every week's lecture videos, and you can access all of these one by one. So uh, is there any doubt in this, Saki? So, and all of these problem solving sessions will be announced to you on this forum only. So like this is a reminder for the problem solving session which we are having today. So this reminder was posted, I think, yesterday. This is the link to join, and yeah. Oh, you meant in the case of submitting assignments. Uh, uh, okay, so Karpa Gum is saying that you find that lecture material is not made available for the learners. I don't think that's the case, Karpagam. So, uh, okay, so maybe the lecture slides are not available to you guys, but you can just go to these lectures, and these lecture videos are anyways available, right? So you can go to these videos also. Probably these presentations from which the profs are teaching, these presentations are not made available to you guys, but yeah, it's up to prof if they want to make it available or not. But yeah, but at least if you want to go through certain topic again, you can just rewatch the video and go through it. So yeah, lecture slides are not available, but this. So and okay, so Zaki is also asking, you meant in the case of submitting assignments and stuff. Okay, so I don't really know if there's any assignments in this course, Zaki, because, like, okay, if there are any assignments, like, this is my first time also, like, while handling assignments for a course. Like, usually in the previous courses which I have done, only like there are these weekly quizzes. So these weekly quizzes, these assignment one, assignment twos. Like, I don't know about programming assignments, but at least uh, these are some like quizzes which you have to submit every week. So how do you submit this quiz? So you only get one chance to submit this quiz. So there are like these 10 questions which are I think same for everyone, and you have to just select the correct option, like whatever the correct options are. And as soon as you click submit answers, uh, your final score will show after the due date of this quiz. So you can submit as many times as you want. So suppose I submit sir. Okay. So like the due date for this quiz is 6th August. So you have to submit it before 6th August, and you can submit any number of times. Suppose I submit this quiz with any arbitrary number, any arbitrary options. So yeah, these are most. So these quizzes are at least MCQs. I don't know if there are any programming assignments. I don't think usually we have programming assignments in an NPTEL course. Yeah. So as soon as I submit, yeah. So answers are submitted, but the actual correct answers and the marks which you got for this assignment will be seen only after the due date, which is this. Yeah, Zaki. So in Swayam, assignments are mostly in the form of quizzes only, because usually there are a large number of learners enrolled, and we really can't have programming assignments to test those guys. Although like I'm not really sure, like I'm just speaking from my previous experiences of TAing these swam courses. Maybe in this course there are some form assignments which I'm not aware of, at least till now. Like, I'll also be seeing this course as it goes along, like what's in the instructor's mind or something. But it's very in with very high likelihood there won't be assignments. Like, I think there won't be much assignments. Okay, like any programming assignments at least. Yeah. So okay. So Archegol, so you are saying that is there a possibility to change time or day of this session because it has a clash with computational complexity? So actually, I don't think we can change the time, but the all these sessions, all these problem solving sessions, Archegol are like uploaded on YouTube. So I'll upload the recording of the session on YouTube, so you can watch. So if you happen to miss out on something which you wanted to, which on the session which you wanted to attend, so you can just rewatch it on YouTube. And these YouTube URLs will be made available to you in due time, like in like day or two. So rest assured, like, so whatever we'll be discussing, okay. So yeah, so whatever we'll be discussing today, like even the even the questions, like even the problem sheet and the problem sheet which we'll be discussing today, and even the recording of the session, all of this will be I'll make available to you guys in a day or two. So don't worry, even if you like happen to miss out on this, like you can like watch the recording. Although obviously it's much, you would also prefer to be present in the session live, but like at least there are a lot of NPTEL courses going on in parallel, so there is a very high likelihood that some will always have clashes. So we can't really do anything about it. The best we can do is make the recordings, video recordings available to you guys. So yeah, so Karpagam, as coming to your questions, yeah, like uh, I don't think much can be done about like the slides not being available publicly, because like it's really up to the professor who's teaching whether they want to make it public or not. Rest assured, they have uploaded they will definitely upload the recordings. And for these problem solving sessions, at least the problem solving sessions which I'll be interacting with you guys in these sessions, at least like I'll be uploading whatever we discuss today on like Google Drive or something, and I'll provide the drive link to you guys. So at least all these problem solving sessions, all of the material which will be covered here will be available to you guys. And like before starting almost every problem solving session, we'll have a short like revision session of all the stuff which was covered in the week of that session. So like today I'm planning to like first of all, like, so the first week's lectures were mostly based on introduction to social network analysis. So first I'll just maybe uh, cover again some of the important definitions regarding social network analysis, which were discussed in the lectures for like 15 minutes, and then we'll go on to problem solving. So even though you don't have like lecture slides available to you guys, but I think you still have a lot of material available to you. So I guess it's fine. I don't know. Okay, so Chirag, you are asking, would it be possible to build social media apps like Instagram and Facebook after this? So Chirag, just to answer this question, so these social media apps have a lot of things going on in the background, right? There are these. So first of all, they have this their front ends, which are like very interactive, which makes them really popular. Like how the apps looks like, what is the UI of the app, and then there is a back end. In the back end, there is stuff like, okay, how do you show recommendations to someone? What recommendations to show to someone? Like how to model like friendships between people and stuff like that. So I believe at least you would be able to like, I don't know, like the coding part is definitely up to you guys, but at least the theory part, the like how do you uh, do things in the back end, the theory of the back end, like how to what recommendations to show, or like some analytics stuff, you would definitely be able to do. So like for building social media apps, you need a lot of further insights. Like first of all, I think in the social media app, the most interesting aspect is like the UI, because like a lot of people would know how to do like social network analysis, but the UI needs to be catchy as well. So that all that things are like, we won't be teaching UI and stuff, but the theory, whatever goes in the back end, like like at least you'll get a at least you'll get a good idea of what goes on in the back end of these kinds of websites. So yeah. So like not completely, you can't completely build social media apps out of this course, but you'll definitely gain a lot of insights on how to build one. And note that this course is not just about like building social media sites, it's about like modeling networks and analyzing them. So it's not relevant just to social media, as you may have seen in the lectures. It's relevant to more general things like modeling diseases, modeling healthcare systems, like almost everything in the world can be modeled as graphs. So there's that. Yeah. Okay, someone, I'll start the problem solving session. It's just that some people have queries, so I have to answer those queries before starting. So yeah, we'll get started with. Okay, so Chirag, I think these kinds of questions of like which language to build a social media app and something is, I don't think I am qualified enough to answer these kinds of questions, because I don't really have much idea of development. I think uh, like let's stick to the course content, which is more theory based and not like this UI and everything based. I think these things can be learned by yourselves, but uh, you need like some mathematics going into the backend, and that mathematics is what we are going to be discussing in the course. So let's stick to the mathematics of it. Okay, so I guess we are done with like I think all the introductory questions. So maybe uh, yeah, I'll just stop this, and maybe I'll just start the problem solving session then. So let me. I have prepared a bunch of questions. So let me just share my screen, guys, and we can get started. Uh, yeah. Uh, Okay, so I hope my screen is visible to everyone. If there are any issues with my mic or my screen, please let me know via chat, so that yeah, so that I can try to fix that. So maybe yeah, let's just get started. So maybe as I said earlier, like we'll start with maybe summarizing the main things which were discussed in the first week, and then we'll like go on to discuss. So we have a bit of summaries, and then we have a bunch of problems which we'll be discussing later on. Okay. So maybe let's just get started with like okay, so the course is about really like social network analysis, and I think the most important part of it is like network. And so what is generally a network? This was covered in the lectures itself. Like, so a network is a graph on like vertices and edges. So v is a set of nodes or vertices, and e is a set of edges, or sometimes called a link. And these and there are like various types of networks. So you may have come across like type of the networks as being so undirected networks, so directed networks or hyper edges. And similarly, like, so there are various types of networks, and like nodes and links with attribute features like weights, timestamp, textual features, etc. So these kinds of things were discussed in the lectures also, like what different kinds of networks are there. I'm not going into the details of it because I think you guys have already, I'll always assume before starting that you guys have gone through the week's lectures before coming to this problem solving session. So yeah, and then there can be self loops and there can be parallel edges in a network. Yeah. So some examples are given here of some networks. Like this is a simple graph. Similarly, if you like a simple graph is someone where the edges are not directed and like there are some vertices, and then a directed graph is where edges also have some directions, like going from one vertex to the other. And then you can add some weight to the edges, and this becomes a weighted graph. Similarly, if you add some loops and something, it becomes like a graph with loops or like parallel edges. Yeah. So yeah. So as I discussed, Soumya, so it's good that you have gone through it, and like as I said, like I'll try to revise some of the concepts which I thought were the most important takeaways from that week's lectures. But I can't go into really everything, right? Because this is just a 2 hour session, and I can't cover like 3 weeks of content plus some problem solving in all these sessions. But yeah, so that's why I'll just be going. I'll just be revising on a very high level, and I hope like these are the most important takeaways from these lectures. So yeah, so I think as little networks, the key takeaway is so a network is nothing but an ordered pair on v comma e, where v is set of vertices and e is a set of edges. And now like why are there different types of networks? A network is just a pair of vertices and edges. So there can be like different types of edges. Some edges can be undirected, directed, hyper edges, etc. And this gives rise to various types of networks. So yeah, and then we have like how do we actually represent a network? So in a computer you can't store a network like these drawings, right? So these drawings are for human understanding, but while you are storing it in a computer or you are giving it as an input to some kind of an algorithm, you can't just really uh, give this drawing as an input. You have to have some mathematical representations for these objects. Like these objects what we have described networks, we have described them like on a very high level, but we need to store these also. So like how do we store these like instead of drawings, because like you can't just input this drawing as a network. So usually networks are represented like these are the two most common methods for network representation, which are like adjacency matrices and adjacency lists. So what are these like so you may have all you some of you guys may already know this, but yeah, it's still something which is very relevant to like networks. Like how do you store the networks actually matters a lot in a lot of algorithms which go into it. Like sometimes like adjacency matrix is useful, sometimes adjacency list is useful. So adjacency matrix of a graph is a square matrix of dimension v cross v, where v is like this mod v is like the number of vertices in the graph, such that each element aij indicates existence of an edge between nodes vi and vj, and also the weight corresponding to that edge in a weighted graph. So what's an adjacency matrix representation? So it's nothing but, so suppose you are given a graph. So suppose you are given this graph of on like 1, 2, 3, 4, 5 vertices, and now you want an adjacency matrix representation for this graph. Then you just draw a square matrix and n like v cross v matrix. So where here number of vertices is 5, so you draw a 5 cross 5 matrix, and you see that like the 1 comma 1th entry, the top left entry of this matrix, will be 1 if there is an edge between like the vertices 1 comma 1. So if there is a self loop at 1, then the value, if there is a self loop at node 1, then there should be a value 1 at this node, at this point. But note that there is no self loop, so this value is 0. But note that there is an edge between 1 and 2, so the 1 comma 2th entry will be 1. Similarly, this 1 comma 3th entry is 1 because there is an edge between 1 comma 3. So this 1 comma 4th entry is 0 because there is no edge between 1 comma 4. As you can see, there is no edge between 1 comma 4. And similarly, there is no edge between 1 comma 5. That's why this entry is 0. And as you can see, like you can build up the adjacency matrix for this graph. And now suppose if I add some weights to these edges, then all the entries like which were 0 remain 0 only, because these edges really don't have any weight. But the edges which had some weight, so like you just replace their entries by their weights. So like between 1 and 2, there was a edge of weight 8. So you have like an entry 8 in like, you have value 8 at 1 comma 2 in the entry. Similarly, this 3 implies that 1 comma 3 edge should have a weight of 3, which is the case here. And as you can see, actually, so there is a very interesting property related to like adjacency matrices of undirected graphs. So you might see that here the edges are don't have a direction. So you can say that this edge corresponds to the edge 1 comma 2 as well as 2 comma 1. So as you can see, the 1 comma 2th entry is also 1 and 2 comma 1th entry is also 1, because there is an edge between V2 and V1 as well as V1 and V2, because this is an undirected edge. In a directed edge, you could have like different representations. Suppose this edge was directed from 1 to 2. Then you would have said that there is an edge at 1 comma 2 because there is an edge from 1 to 2. But the 2 comma 1 entry would have been 0 in that case, because you would have said that okay, so there is really no edge going from like 2 to 1. There's only an edge going from 1 to 2 if this edge were directed like this. And then like this entry would have been 0, and whereas this entry would have remained 1. So there is a distinct, like not necessarily a distinction, but like yeah, this thing you have to keep in mind that like even though there is a single edge, like in adjacency matrix here, like in undirected graphs, you have like two entries as one corresponding to that edge. Similarly, for this 1 comma 3 edge, like it can also be thought as 3 comma 1 edge. So 1 comma 3 entry would be 1, and similarly 3 comma 1 entry would be 1. So as you can see, like I'll just maybe discuss this also. So the adjacency matrix for these kinds of graphs, which are like undirected graphs, this adjacency matrix has a very special property, right? If there is an edge between I and j, then the I comma jth entry will be 1, and v and j comma ith entry will also be 1, right? If there's an edge, suppose between 4 and 5, then 4 comma 5 entry will be 1, and 5 comma 4 entry will also be 1. So this adjacency matrix really has a very special structure. And what are these matrices called? So if you this and this you guys must have studied in high school also. So what are those matrices called in which I comma jth entry is equal to j comma ith entry? Would anyone like to answer this in chat? Just think about it for a minute, guys. Like, so basically the question is like uh, the adjacency matrices for the undirected graphs have a special property, have a special structure. And what is this called? Okay, so not exactly triangular matrix, Goel. So triangular matrices are matrices in which like uh, one like in which lower triangle or upper triangle has all entries as 0. But note that like this is, suppose this is an adjacency matrix. As you can see, like in the upper triangle also there is like all entries are not 0, and in the lower triangle also all entries are not 0. There are some entries with value 1. But yeah, like actually, yeah. So Tejas is saying it. So good job, Tejas. So Tejas is saying that these are called symmetric matrices. So yeah, exactly. So so these kinds of matrices, so adjacency matrices for interactive graphs have a special structure which is symmetric matrices. And what are symmetric matrices? So like symmetric matrices are matrices which in which I comma jth entry of the matrix is equal to j comma ith entry of the matrix. And intuitively, what this says is that the upper triangle of the matrix. So this is the upper triangle is actually like if you reflect this triangle along like so if you reflect this upper triangle across this principal diagonal, then you get like the adjacency matrix back. So actually, what this implies is that you don't really need to store like all these lower triangle entries. These lower triangle entries are just equal to like the upper triangle entries. So if you reflect these upper triangle entries along this principal diagonal, then you will obtain the lower triangle entries of the matrix. So really like so there's this so this matrix has n square entries, but out of that you really just need to store these like n times n plus 1 by 2 entries. You don't really need to store the lower half. You just need to store the upper half. So yeah, so good job, Tejas. And yeah, okay, Goel, I understand like so that triangle so I think you meant to say that the adjacency matrices can be represented by triangular matrix, which is completely correct in its own right. That we don't really need to store this whole matrix. We can just store one triangular matrix, like the upper triangle, or like let's say the lower triangle only, and we will have information about the whole matrix. So yeah, okay, so there's that, and yeah, so we are discussing this about this adjacency matrices, and then we have this adjacency list. So what are adjacency lists? So as you can see, like sometimes a matrix might be sparse, and what I mean by sparse, so as you can see here that so you have these n square entries in the matrix, but out of those there are only like 1 2 3 4 5 6, 1 2 3 4 5 6. So there are only 6 edges here out of like possible. So maximum possible edges in this graph would have been 5 choose 2, which is like 10. So there are maximum 10 possible edges in this graph, like, but there are only actually 6 edges present. Like as you can see, the edge 1 comma 5 is not present, 1 comma 4 is not present, and similarly two more edges would be there which are not present. So saving this, so trying to use maybe like n square space to store this kind of a graph when there are like less than n square edges in the graph might be a waste of space. And that's where this adjacency list comes into the picture. So while storing the graph as adjacency list, so what you store is for every node, you just store the neighbors of that node. So basically, you just store the vertices which have an edge with the vertex for which we are storing the list. So for the vertex one, as you can see, we have 2 and 3 as neighbors. So only one has edges with 2 and 3. So you just store 2 and 3 for this one. Similarly, for this vertex 2, you just store the neighbors of this vertex 2. For vertex 2, the neighbors are like 1, 3, 4, and 5. So you would store 1, 3, 4, 5. Similarly, for vertex 3, the neighbors are 1, 2, and 5. So these are 1, 2, 5. For vertex 4, there are 2 and 5. Similarly, for vertex 5, they are 2 and 4. 2, 3, and 4. So as you can see now, you just need to this adjacency list can be stored in like smaller amount of space. Like we just need to store 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We just need to store something like 14 entries, whereas here we needed to store 1, 2, 3, 4, 5, 5 times 9, which are 25 entries. So uh, adjacency list notation is usually more space efficient, but then like there are some trade-offs. Like you might think if adjacency list is always taking lesser space, then why don't we always just store every matrix using adjacency list? why do we use adjacency matrices at all, and it will become clear to you guys in due time, or like some of you already might know this, that like these also have some purposes, like these adjacency matrices are also very useful. So yeah, so even though adjacency lists are space efficient, but sometimes adjacency matrices are like more time efficient, if I have to say so. So something like that. So maybe we'll come to that a bit later in the course, or maybe later in today's session itself. And then in the lectures, I think the last thing which was discussed was like one of the last things which were discussed was like various kinds of network categories. So, so you have a network and you have to analyze the network, right? But you first need to know what type of network is it. So there are various categorizations for networks. So this was also discussed in the lectures. So there is a link centric view. So what does link centric actually mean? Like why are these like definitions? So maybe I'll just make them a bit clearer. So what does link centric mean? That you are categorizing the network by looking only at the links. So link is just a synonym for edges. So this can be also said as like edge centric. So you can have a like link centric view of the network. So you only look at the edges of the network, and that's how you categorize the network. Like suppose you are given a graph G, and you have to categorize what kind of a graph it is. So if you have to categorize just looking at the edges, then you can have these kinds of characterizations which are unipartite, bipartite, or sign. Like these, note that this is not an exhaustive list of categorizations, but like this list like covers a great deal of graphs, like great amount of graphs, which we'll be seeing over this course. So yeah. So like unipartite would be where like edges really can be between any two vertices of the graph. Bipartite is like where there is a partition of vertex set, such that an edge only goes across the partition always. Like an edge cannot be present in like one of the sets of the partition between two vertices of the same set of the partition. Similarly, signed is like you look at the edges and every edge has a sign, like a positive or a negative sign. So if that's the case, then you call that a signed network. Similarly, if you are looking both at vertices as well as edges, then like there are some other kinds of characterizations which are like, present for the class, which are like homogeneous, heterogeneous, attributed, multidimensional. I think this was covered in the lectures also. So like homogeneous is where like all the vertices have the same type, edges are the same type. Heterogeneous is something where like vertices can be of different types, edges can be of different types, and so on. Attributed is where like every vertex of the graph has some attribute attached to it. Multi-dimensional is maybe a graph which is spanning across like various dimensions. So, so yeah, just giving a summary of everything, not going into detail, because in detail it was discussed in the lectures itself. Similarly, local view, like in a network, a local view is something where you are just looking at like something very local, like something like a vertex or like a pair of vertices or a vertex and its neighbor. So you're not looking into the graph as a whole, but you're looking individually at every node and forming your like algorithm based on this. So for example, like suppose you have to analyze population of a country. Like I'm just giving a very high level example. Just hear me out, guys. Suppose you have to model like the literacy rate of like India. Suppose you have to map out like literacy rate of India, or maybe not like literacy rate, but mm, yeah, maybe political preference within so suppose you are like you're surveying people and you're looking at like political preferences of people across whole of India. So you can think of like the country as a whole, and then like maybe you can have like every vertex will represent something in the graph. Every vertex will represent one of the people, like one of the person of the population, and then maybe the graph has edges, and like there will be like some other kinds of like vertices or let's say edges which will represent the political alignment of the person. Like I'm not really sure, but yeah, there can be something. So if you're looking at the population as a whole and analyzing the data, So one way is like you look at the population as a whole and analyze the data. Another way is like you look at specific people or like pair of people who are nearby, and then analyze the data for these specific people, and that's what is called a local view. So a global view is where you are looking at the whole population together, whereas a local view is something where you are really looking at some specific people, like inside. So you're looking at some specific vertices. And here, like a categorization is egocentric, which was also discussed in the lectures. Similarly, there's a temporal view in the network. So networks which change over time are called temporal networks. So yeah, this is another kind of characterization. And then if you want to generalize everything, then there are like hypergraphs. So what are hypergraphs? Hypergraphs are a very interesting and mathematically like a bit harder things, at least to me. So here, like in a network, we just described edges as being between two pairs of vertices. So here we only said that, like in the examples we discussed, edges were only between two sets of vertices, a pair of vertices. But like in what are hyper edges? So if there are edges like so if one edge spans like multiple vertices, more than two vertices, so you can think of this. Edge as covering these two vertices. A set of these two vertices is what this edge denotes. But suppose in like what are hyper edges? So hyper edges can like cover more than two vertices. Suppose I take these four vertices, and this can form a hyper edge. Like this set of vertices is a hyper edge. Like so, this set of vertices is a hyper edge in a hypergraph. So yeah, if there are hyper edges present, like then that graph is called a hypergraph. So this is also like uh, useful in like practical purposes. So we have like a bit of questions prepared for these kinds of things also. So maybe you guys will appreciate it a bit more after like we discuss some of the problems. So okay then. So does anyone have any doubt till this point? If there are any doubts, like you can feel free to type out in chat, and like I'll try to answer them to the best of my capabilities. And also yeah, maybe I just forgot to mention it. So like I believe like audio and video for you guys has been disabled, but like if you guys have doubts at any point, like feel free to stop me and ask your doubt in the chat. You don't need to me to finish the topic or something, or ask you specifically if there are doubts. If there are doubts at any point, just ask them straight up. Like, I'll be happy to answer them. Okay then. So are there any doubts till now? Anyone? So, like, if there are no doubts, then maybe we can proceed to like discussing the problems. Yeah. Okay. So good sound. So far so good. Okay. So yeah, like since no one has like asked any doubts in chat, I'll assume that it's clear to everyone, and maybe now we can move on to the questions. So first question, and like I'll prefer if you guys answer these questions for me. Like, I have prepared these questions as like practice questions for you guys for the week's assignment. So these are not exactly the assignment questions, but questions which are quite similar to assignments. And if you solve these, you will be able to like with very high chance like you will be able to solve the assignments also. So okay, so okay, RP Goel I think is asking in the chat. Okay, so what's a hypergraph? So as I said, RK Goel, maybe so hypergraphs are something which have hyper edges. And what are hyper edges? So right now, what we so in these kinds of graphs which we have modeled, we have described that an edge is like between a pair of vertices, right? So you can think of an edge as being okay. Maybe I should this kind of labeled vertex. So suppose in this graph, the edge can be thought of as a pair 1, 3, right? So 1, 3 can is an edge in this graph. Similarly, 1, 2 is an edge. 2, 5 is an edge. 4, 5 is an edge. So like any set of two vertices, an edge is just a like set of two vertices. Like this edge is just a set of like two vertices 2 and 5. This edge is a set of vertices 1 and 2, and so on. Uh, But in a hypergraph, like what's in hyperedge, usually we won't be discussing a lot about hyperedges, but they are they are also super important in practice as well as in theory. So like suppose the graph had uh, it's right now we are just saying an edge as being like a set of two vertices, but why just stop at two? Like maybe let's just say we have edges which contain three vertices. Like suppose 1 2 3 is an edge, then this set, then that hyperedge will be denoted by this set 1 2 3. Similarly, you can have like 1 2 5 4 as an edge, so then this set of vertices will be a hyperedge. So hyperedge can be thought of as a set of vertices where the set size is greater than 2. So usually, I think this is a good definition to keep in mind that a hyperedge is a set of vertices uh, of size greater than 2. And if the graph contains a hyperedge, then that is called a hypergraph. Usually, we won't deal a lot with hyperedges and hypergraphs, at least in this course, but yeah, they are things which they are also very important. So these are not just theoretical concepts; they are used really in practice also. So yeah. So yeah, the main idea for describing hyperedges is what's so special about the sets of size 2? Like why are we just stopping at 2? We need more than 2 for some reason. And that's where hyperedges come into picture. Okay, so how does it differ from transitivity of edges? So what do you mean by transitivity of edges, Archikoil? I'm not really sure. I don't think edges follows any transitivity. Like here, 1 comma 2 is an edge, 2 comma 5 is an edge, but 1 comma 5 is not an edge. So why are edges transitive? As for example of hypergraph, yeah, so a set having more than two vertices is hyperedge. So benefits of that, so it can help us model a lot of situations. So you'll come across one of the questions in which actually hyperedges will be used. So as you so some uses of these hypergraphs are described in the lectures also, and we'll also see like I think in the fifth or sixth question we'll see why is hyperedge important. So just wait for maybe a bit, and then you will see why are hyperedges beneficial. So sometimes so the main high level idea is sometimes just size 2 edges are not sufficient to model a real world network. Sometimes the real world networks actually needs more than sets of size 2 for modeling, and this is completely believable, right? Why do we need just sets of size 2 to model real world networks? Maybe we need more, and we'll discuss one such example as we move along these questions. Okay, so till then maybe we can okay, I think it's the fifth or sixth question that we'll be discussing. But before coming to those questions, let's just discuss the questions from the start. So yeah. So as I said before, I'll like you guys to try to answer these questions first. So social network analysis cannot be used in the healthcare domain. So is this statement true or false? I think first few questions would be very easy questions for you guys to solve. I believe these are more warm up questions to make you guys appreciate why are social networks important. Yeah. So as Saumen, Karpagam and Tejas are saying, so good job guys, as well as Mohammad Zaki, that actually this thing is false. Like actually this thing is false because social network analysis actually can be used. So focus is here that here the statement is saying that it cannot be used. So this statement is false. Uh, as one can use social network analysis to model and then analyze uh, like like infections population. So something like that. Like uh, one can use social network analysis to model and then analyze infections in a population. Like how is the infection growing? Like what are the properties of infection? Like the rate of growth of the infection in a population and stuff like that. And I think this was covered in the lectures also, as discussed in the lectures. So good job, guys. At least like you guys are paying attention. So like because note that sometimes these kinds of questions can like if you like just skip this word cannot and you just say like social network analysis is used in the healthcare domain and you might just like at least in the like quizzes you might answer this as true because like you did not focus on this cannot like yeah, not really necessary, just a like thing to keep in mind while answering the questions, not really a like theoretical thing to say, but yeah. And now maybe like second question is a bit more interesting. So so there was this egocentric view discussed in the lectures. So what will be the egocentric view with respect to node 3 in the given network? And as you know, as you might remember, in an egocentric view you have a node which is the ego node. So here we are saying that suppose the ego node is 3 and then there are alter nodes. So if the ego node is 3, then what will be the alter nodes and what will the network look like with respect to node 3 as the ego network? So like maybe can someone answer like which nodes will be the alter nodes if node 3 is the like ego node? Okay, so Someone is saying that 4 will be the alter node. So just 4, or will there be more nodes which will be alter nodes? Okay, so Karpagam is saying that alter nodes are 2, 4, and 7. So 2, 4, and 7. And just these three, or like are there more alter nodes? Yeah. Okay, so node 5 is also alter node, and 5 and 1 as well. So yeah, Karpagam, right. So as Someone and Karpagam collectively answered, like so these 2, 4, 1, 5, and 7 are the alter nodes. So basically, this question was more about like knowing the definition of egocentric view of ego nodes and alter nodes. So what are actually alter nodes? Just maybe to make it clear to everyone, like what are alter nodes? So if you have an ego node, so here the ego node. Okay, so Tejas is saying except 6, all nodes are alter node. So that's really not true. Tejas, node 3 is also not an alter node. It's the ego node, right? So really the alter nodes are 1, 2, 7, 4, 5. So except 3 and 6, all nodes are alter nodes. So just saying except 6 is wrong. I have to say except 3 and 6. I hope it's clear. So what is the definition of alter node? So if you have a ego node, right, like whatever node is the ego node, then all the immediate neighbors of that node are called alter nodes. So what do I mean by neighbor? So neighbor is just vertex which shares an edge. And right now we are just talking about normal graphs, not hypergraphs. So like for the node 3, you can see that 3 shares an edge with 2, 3 shares an edge with 4, 3 shares an edge with 1, 3 shares an edge with 7, and 3 shares an edge with 5. So these 5 will be the alter nodes, 1, 2, 4, 5, and 7. So answer will be nodes 1, 2, 4, 5, 7 are alter nodes as the ego node 3 has an edge with all of them. Okay, and what does the ego? What will be the egocentric view of the network? So note that what is egocentric view of the what does egocentric view of the network mean? So it means like just form an induced subgraph on the ego nodes and the alter nodes, and this is what you call the egocentric view. And what do I mean with by this? Like draw induced subgraph. So just consider the vertices which are like alter node and ego node. So here the vertices will be like 1, 2, 3, 4, 5, and 7, and like everything except vertex 6. Just consider those sets of vertices, and then just draw the graphical tree. Or maybe you can just say like delete every vertex which is not a like ego or alter node from the graph, and the graph which you obtain later will be the egocentric view. So here, if you remove this vertex 6, so maybe I should just copy and try to crop this. I don't know if it will work. So if I try to crop this, yeah. So maybe I need to do something. Okay, maybe I'm not able to do that, but yeah. So maybe I'll just post the image of the egocentric view later, or maybe I have. Can try to do this. Okay, maybe we should not discuss this. Yeah. So just like what? So I'll post the like I'll post after this lecture like the image which is the egocentric view. But know that what will be the egocentric view. So every edge, like all of these edges will be preserved. Just this six vertex 6 will get deleted. So as vertex 6 is deleted, the 6, 5 edge also gets deleted. So everything except the vertex 6 will form the egocentric view of the network with respect to node 3. So note that yeah, Saman. So yeah, it's difficult to crop it right now, but I'll do it and like yeah, upload it later on. So no worries there. But like so note that like all of these edges, like even these edges, like one the edges between 1, 2, 4, 5, all of these are also preserved in the egocentric view. So basically all the ego nodes and alter nodes are preserved, and all the edges which are between these ego and alter nodes are preserved, and everything else gets deleted in an egocentric view. So here node 6 and this 5.6 that gets deleted, and everything else becomes the egocentric view. So yeah, maybe I should just maybe okay, maybe like I think this is the correct answer. So yeah, maybe I should just deny this answer. Okay then, so this was more about like revising what are ego nodes and alter nodes, and maybe getting a pictorial representation for them. And now maybe let's move on to the third question. So third question says that what is the time complexity to check if an edge exists between two vertices I and j using an adjacency matrix? So here is where these kinds of questions is where it will become clearer to you guys like why our adjacency matrix is important also. Like like even though adjacency lists are like space efficient, adjacency matrices are actually time efficient. So what do you guys think? What is the time complexity to check if an edge exists between two vertices I and j using an adjacency matrix? So would anyone like to answer this in chat? So adjacency matrix just shows like for any entry, like if you have to check nodes I and j, like if there is an edge I between nodes I and j, you have to check the I comma jth entry of the matrix. If it is one, then okay. So Karpagam is saying that the time complexity to check if an edge exists between I and j in adjacency matrix is order n. So doesn't everyone agree with that? Maybe like I'll give you guys a couple of minutes to think about it. Like note that so you are given this kind of a matrix you have stored this kind of a matrix, suppose in form of a 2D array, and then you have to check if the I comma jth entry is 0 or 1. If the I comma jth entry is 0, then you will say that there does not exist an edge. And if it is 1, oh yeah, so Karpagam is saying that we all, if we already know where I and j exists, then it could be order 1. So yeah, definitely. So it is actually order 1 Karpagam. So note that whenever we are talking about adjacency matrix, we are storing it in form of like an 2D array or something. If we are talking about implementation part of it, so if you are storing like it in form of 2D array, then you just need to like access the I comma jth entry of that array, and that can be accessed in like constant time, right? Not a one time. So that's why like you can access it in order one time, and if that entry is 0, then you say like if there does not exist an edge, and if the entry is 1, then you say that there exists an edge. So note that this comparison of 0 or 1 is also in order one time. Okay, so Somen is asking for a 2 minutes break. So sure, someone maybe like just after I finish writing this question, we can have a 2 minute break and then start discussing again. Maybe I'll just write down the answer for this. So Karpagam, good job. So the answer is actually order 1. As uh, we need to check if I comma jth uh, yeah, if I comma jth entry is 1, then it exists, or 0, it does not exist. And note that like, but if you actually had like a adjacency list instead of an adjacency matrix, if you have an adjacency list, then you have actually just stored like the list of edges with which you have an edge, but you have to go through this list one by one. So to check from I if there exists a vertex j, you have to access the list one by one. So you just first check the first entry whether it is the vertex j. So you go to the vertex i's list and you check if like j exists in that list. And how to do that? You just go to the first element of that list, check if it is 0, like check if it is j. You go to the second entry, check if it is j, and so on. And note that there could be potentially like j could be right at the end in this list, and like there could be potentially order n element n vertices in this list. So that's why like checking this thing in like adjacency list takes order n time, because we don't really know like where would j exist in an adjacency list. But in a like adjacency matrix, we already know where I and j exists. And this is kind of the trade-off which happens between like matrices and lists. Like even though you are saving space in the list, but you're saving that space at the cost of some additional time for some operations. So like this operation can be checked in like order one time for adjacency matrices, but it will take order n time for adjacency lists. So I hope this is clear to you, Karpagam. And now maybe we can take a like 2 minutes break. So it's 7:12 right now. We'll start again at 7:15. So I'll mute myself till then. Okay, so maybe we can start again. So yeah. So maybe now let's just come to the fourth question. I assume that answer three was clear to everyone. So what is the space complexity of the adjacency list for a graph V with V vertices and E edges? So would anyone like to answer this in chat? Like, so you what is the space required to store an adjacency list? So note that what kinds of things are we storing in an adjacency list? For each vertex, we are storing the neighbors of that vertex, right? So what would be the what would the space taken for this adjacency list? Okay, so good job, Vikas. So Vikas is saying that the space required will be order of V plus E. So yeah, so exactly that's correct. So good job, Vikas. So note, so guys, note that one might think that okay, like okay, so why is this? How do I want to go with this? Okay, so maybe yeah, because you are saying that it will be order V plus E, but maybe like let us try to present some argument and like which is incorrect, but we'll still try to see like let's try to figure it out by ourselves that why would that kind of an argument fail here, or like why would that kind of an argument would not be optimal, like just for understanding. So what I'm kind of saying here is that okay, so how do we store this adjacency list? So for every vertex, what we are going to store is we are going to store like all the vertices which have an edge with it, right? And the maximum number of vertices which can have an edge with vertex 1 would just be like equal to maximum number of edges which are possible. So there are order e number of edges can be present in like one's list, right? Because like suppose all the edges are originating from one itself, then the length of the list for this vertex 1 can be e. And by similar argument, length of the list for this vertex 2 can also be E. For the vertex 3 will also be E. For vertex 4 will also be E. And if we go until vertex n, so there are n vertices. And for all the vertices, like the length of these lists will be, maximum length will be E. So then if there are V vertices and like each vertex has a list of size maximum E, then the space should kind of be equal to V times E, right? So it should be like if we do it by this kind of analysis, then it should come out to be order V times E. But like I think I've already told that it is actually equal to order V plus E. So where do you guys think is this like kind of argument suboptimal? Like when I'm saying that okay, that list one is of size maximum E, list two is of size E, till list V is of size E. So total element stored is like V times E. So why is my argument like why is this coming out to be V times E, like it's not incorrect, like it will the space like V plus E is already less than V times E, but why is this V times E calculation suboptimal? Would anyone like to point out in chat like why is this like V times E the kind of the way I did my calculation, like how I calculated is like first list is of size E, second list is of size maximum E, third list is of size maximum E, and so on. There are V lists, so V times E. I place an upper bound of V times E. Why is this upper bound suboptimal? Maybe because since you answered like the correct bound, which is V plus E, can you point out like why is this V times E bound suboptimal? Like where is my argument? Like what is suboptimal in my argument? Like because usually what I think is like it's good to know the like it's good to arrive at the correct answer, but we should also know why an incorrect or maybe a suboptimal answer was actually suboptimal. So like, why is the argument like this? Is how we can understand things much more deeply. So where is my argument being suboptimal? Like when I am saying that every list is of size E, maximum E, and so like there are V such lists, and so the maximum size will be V times E. So I'll give you guys maybe like 2-3 minutes to think about it. So anyone, Vikas, maybe would you like to? Okay, maybe since no one is like typing chat, maybe I'll just cover this kind of an argument. So guys, while this argument is true that like length of each list can be like E, and so like one bound which can be derived is V times E, but we can do like some better bounds because like if I'm counting it in this manner that suppose here the length is E, 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 and so on, then I'm actually kind of over over counting over counting the number of edges. And why is that the case? Because I know that if like suppose one has an edge with 2, then I know that only 2 can have the end, like only this edge can only occur once after this. Like if this edge, like if this 1 comma 2 edge occurs in one's adjacency list, then it can only occur once more in two's adjacency list. Whereas right now in my argument, what I was assuming was okay, like there are E edges, so like 1 comma 2 is one of those edges, and I was saying that these E edges will can occur in all of the lists. That's why I was saying that here E edges can be present, here E edges can be present, here E edges can be present, and so on. So I was saying that in all the vertices, in list of all the vertices, like E edges will be present. And so I derive the bound of V times E. But note that this is really like I'm overcounting a lot because I know that an edge can occur in maximum 2 lists. Like suppose the edge 2 comma 1 can occur in like one adjacency list as well as 2's adjacency list, but nowhere else. Similarly, the edge 4 comma 2 occurs just in like 4's adjacency list and 2's adjacency list. So it really cannot occur in like every vertices list. Like an edge can occur in only list of 2 vertices. So I hope this kind of thing makes sense. And that's how you derive the bound of order V plus E. So you can actually say that since every edge occurs in like entries of 2 vertices, so basically the total number of entries over all lists will just be equal to 2 times the number of edges, because every edge appears like twice and there are E edges, so 2E will be the number of entries here, total number of entries in this list. And note that after that there can be some vertices which do not contain any entry, but you still need to store the vertices. So that's why you add something like a V to it. So you need to store the vertices which are on this side, so there are V vertices, and then you need to store the edges, which takes like 2V space. Vertices take V space to store and edges take 2E space to store. So which is like V plus 2E, which is just order V plus E. So I hope this makes sense, guys. If it is not clear, please ask me in chat and I'll try to explain it again. Because although this is like the beginning of the course, but like it's better to keep up with all these kinds of arguments, because if you don't get these kinds of if you skip understanding these kinds of arguments, then maybe like arguments later on the course will become a bit more difficult. So that's why it would be preferable if you understand everything right now. Okay, so yeah, so maybe like if there are no doubts in the chat, I'll just try to say what a V plus E. And why is the case? As we need to store every vertex, and uh, for every edge there are two entries. Wait, for every edge you complete, there are two entries in the list of vertices u and v. One is in the hence total space taken is v plus 2v, which is something like order v plus. So I hope everyone is comfortable with these big O notations, this theta, big O, and like gamma notations. And so, yeah. So okay, there is if this is clear to everyone, like I'll assume it is clear since no one is asking in chat. Okay, so Sai Mohit, do you have a doubt here? So you have raised your hand. You can ask your doubt in chat if there is any. So Sai Mohit is asking some doubt in the chat. Okay, so uh, I'll just give a brief. Okay, so Sai Mohit, you have joined the class late. You're traveling, so if you want to recap, so maybe I'll just give a like 2 minutes quick recap because anyways, this session will be going to be uploaded on YouTube later on, so you can watch it in detail later. But for now, just as a quick 2 minute recap of what was done. So basically, first I just summarize like what was discussed in this week's lectures. So basically, in this week's lectures, they have we define what is a network. So network is nothing but an ordered pair of vertices and edges, and there can be multiple kinds of edges like undirected, directed, hyper edges, and so on. So this was basically which we discussed, and then we discussed what are different kinds of network representations, which are like adjacency matrix representation, adjacency list representation, which we're talking about. And then we talked about like different kinds of network categories. So there are different views of categorizing networks, which are like link centric. So link centric is where you just look at the edges and categorize the network. Node centric and link centric is where you look at both vertices and edges. Local view is where you look at something very like small, like one vertex or two vertices or something. Temporal view is something where like the graph changes over time, and hypergraphs are like the generalizations of all these things. And then there were some questions are like pretty trivial. Like first question was just about the uses of social network analysis. So first question just said that social network analysis can be used in the healthcare domain. They're just a very formal function. And then second question was about egocentric view, how do you draw egocentric view for a network with respect to some node? This has been covered in the lecture, so this was just a problem which was an application of things in the lectures. And then we discussed one problem about time complexity to check if an edge exists between what is I and j using an adjacency matrix. So basically, we are trying to discuss like trade-offs between adjacency matrices as well as adjacency lists. So to check if an edge exists between vertices I and j in an adjacency matrix, you just need order one time. But for this checking in adjacency list, you need kind of order n time. So that way, like adjacency matrices are more time efficient for these kinds of queries. But note that adjacency matrices use like order n square space, whereas adjacency lists, as we just described, use like order v plus e space. So adjacency matrices use v square space, but lists use v plus e. So adjacency lists are more space efficient, but sometimes adjacency matrices are more time efficient. So this is a quick recap of what we discussed till now. Now maybe okay. So Sai Mohit is asking, after seeing this problem, would you recommend that we also parallelly learn the graph DSA algorithm would it help? So yeah, definitely, Sai. If you can learn like graph DSL algorithms, at least the basic algorithms like BFS, DFS, or like Dijkstra's, the shortest path algorithm, like, I think it would be really helpful. At least BFS and DFS would definitely, breadth first search and depth first search would definitely be useful to understand the concepts discussed in this course much more deeply. Okay, I think if it's clear, then maybe we can move on to the next question. So, so I think this kind of a question we already discussed. So, how can you represent an undirected graph using an adjacency matrix? So, I think this is more than one option, correct? So, what do you guys think? We just discussed this like previously, how can we represent an undirected graph using an adjacency matrix? So, what do you think out of these OABCD options? Like, can we represent an undirected graph using a diagonal matrix, using upper triangular matrix, using symmetric matrix, using lower triangular matrix? So, what matrices can be? Yeah. So Karpagam is saying that we can represent undirected graph using a symmetric matrix, but just symmetric like okay, like and in like proper definition of adjacency matrix, definitely it is a symmetric matrix which we discussed previously. So I don't really understand. Like okay, if but like if the problem is just asking what's like suppose this was like just one option correct question, then maybe like I would have just said like symmetric matrix because I know like adjacency matrix is symmetric matrix. But how can I represent an undirected graph using an adjacency matrix? So maybe I can also represent it using upper triangular and lower triangular matrices also. Like I said previously that since the matrix is symmetric, you kind if you just store the upper triangular entries, then you automatically obtain the lower triangular entries as well. And similarly, if you just store the lower triangular entries, you automatically obtain the upper triangular entries as well. So just storing maybe lower triangular or upper triangular matrices uh, would also be okay to represent an adjacency matrix. So I hope makes sense. Yes, yes. By symmetric, we mean undirected graphs. In the question itself says that it's an undirected graph. Like because in an undirected graph, like the edge, if I comma j is an edge, then j comma I is also an edge. That's why like, you say that the adjacency matrix of an undirected graph is symmetric. So like yeah, if this question was just maybe one option correct, like choose the best option, I think I would have just marked like symmetric matrix because like adjacency matrix is symmetric. But if it is more than one correct, then maybe I would like from my end mark like B, C, D, both all of these options because like I can represent it using upper triangular symmetric as well as lower triangular matrix. So yeah. So yeah. But at least maybe let's not get into like how to mark or what to not mark, like that's like more exam based view. But from a theoretical standpoint, uh, at least from a theoretical standpoint also we should understand that yeah, using upper triangular matrix is also sufficient to store like adjacency relation in a graph. You don't really need to store the whole matrix, you can just store the upper triangular part or the lower triangular, and that's also perfect. Yeah, so I'm not like really concerned about like what would be the correct answer in an exam, but at least from a theoretical standpoint we should understand what's the correct idea. Correct as a adjacency matrix of an undirected graph is symmetric and hence can also be represented in upper this that. So maybe let's just move to the sixth question then. If it is clear, if there are any doubts here, please feel free to ask me in chat. Otherwise, I'll assume that you're following along. Okay. So the sixth question is, how many edges are there in an undirected complete graph with 19 nodes? So there this is an undirected graph, and what's a complete graph? So complete graph is a graph where every pair of edges, every pair of vertices has an edge between them. So there are 19 nodes. So if you take any pair of nodes, then there will be an edge between those nodes. So how many edges will be there in such a graph? Would anyone know? Okay, so Tejas is saying that the answer would be 18 factorial. Somin is saying the answer would be n times n plus 1 by 2. So I would say that maybe try to think about it a bit more, guys. So, so how many, like, for between, like, suppose there are like 19 vertices, then like so maybe just try, let's start with like maybe just start with smaller examples, like, okay, like Somin, they just like whatever arguments are, maybe just see like for like, does your answer work even for like something like 3 vertices or 4 vertices? Like we know in in a complete graph with 3 vertices, a complete graph with 3 vertices will be just a triangle. So if number of vertices is 3, then your answer, then your calculation should come out to be 3. And I don't think like if I put n equal to 3 in Soman's answer, then it comes out to be 6. Similarly, Tejas, I think your answer would come out to be 2 factorial or something, which is 2. Yeah, so Karpagam and Mohit are saying like it would be n times n minus 1 by 2, which is actually the correct answer, guys. So yeah, so many you were close, but I think you messed up a bit, like plus 1 and minus 1. So actually the answer is like n times n minus 1 by 2. And yeah, this can be like computed like by. So I'll assume that you guys know these like combinatorial equation, like 19C2. So the number of edges will be equal to 19 choose 2. Like C is means the combination, and why is this the number of edges in the graph? So what you're saying is in an undirected, so the graph is undirected. So you really don't have a direction between any edge. So like 1 comma 2 and 2 comma 1 are actually the same edge. So in this, so as I said previously also, so and like these edges in undirected graphs can also be thought of as sets of size 2. So how many sets of size 2 can be there in a graph with 19 nodes? So I just need to choose like from these two, like, so there are like 19 nodes, and I need to find the number of ways in which I can form like sets of size 2, which is like just like I need to choose 2 vertices from these 19 nodes, which is just like this 19C2, 19 and the formula like NC2 is nothing but n times n minus 1 by 2. So this will be equal to 19 times 19 minus 1 by 2. So I hope like you guys are familiar with this 19C2 notation and how I arrived at this, because I think this is just like high school. We at least we studied this in high school, like in permutation and combination. But anyways, like even if you're not clear, just think of it as something like this, that okay, for first node, like there are like if there are 19 nodes and I need to find like the total possible number of pairs, right? So for first node, I have 19 choices since there are 19 nodes. And for the second node, I have 18 choices because now I have picked one node and I need to pick another node. But note that if I just write 19 times 19 minus 1, then I have overcounted some nodes. As in like I have counted like the edge 1 comma 2 and 2 comma 1 twice. Whereas these two are essentially the same edges. So I have to divide this by 2. So that's why this is the complete expression, which is 19 times 18 by 2, which is like something like 19 times 9, which is 190, 171. So this is the correct answer. So does this make sense, guys? In a general graph with n nodes, the answer would be n times n minus 1 by 2. Following this, like n choose 2, which will be n times n minus 1. Does this make sense, everyone? So Vikas, I think you were writing something in chat. So is this clear to you? And like Somen and Tejas, is it clear to you guys? And like also, like if you guys have any doubts, like maybe if you have some doubt in like how you arrived at the expression, like do you want to discuss how you arrived at the expression of like something like 18 factorial, or do you understand the mistake now? I think like not just knowing the correct answer is important, but like understanding why your answer was incorrect is also important. So okay, so if it's fine with you guys, then yeah. So good job, guys. So maybe we can move on to the next question. So I think someone was asking initially also that okay, why are hypergraphs important? So here is like in the seventh question we have like one such like important application of hypergraphs. So co-authorship network. So this was also discussed in the lectures, but maybe we can discuss again. So co-authorship networks can be modeled using hypergraphs. So is this statement true or false? So what are co-authorship networks? So you guys might know like there are research papers, and then in research papers like there can be multiple authors for a single research paper. Like there can be more than like 10 authors or 20 authors even. So now for modeling these kinds of networks, like hypergraphs become much more useful. So yeah, so as someone is saying, the answer is true. So, yeah, so good job, someone. So yeah, so maybe I should just explain. So I was in the middle of explaining. So maybe I should explain. So what's a co-authorship network? So basically, suppose you have a bunch of research papers available, and now you want to model like which research paper has which author, which research paper has which author, and stuff like this. So suppose in the and like and there are like fixed people, like there are some people in the population which can be represented as nodes, and then each research paper can be represented as an edge. And how do I mean? Like okay, so an edge represents like the edge will cover some of the vertices, right? So vertices are some authors. So now like if a research paper is denoted by an edge, like then the authors of that research paper form the vertices of that edge. And note that as there can be like more than two authors, so there can be more than two vertices in an edge, and that's what you call a hyper edge, right? And that's why like this is one application. Like so analyzing so usually like co-authorship networks are also a lot analyzed a lot these days, like to see like what are the trends in research paper writing and stuff. So and what are like important people in research paper writing and all, who are most important researchers and everything. So these co-authorship paper networks play a very important role, and they can be modeled using hypergraph as every vertex denotes a researcher, and each hyperedge denotes a research paper with the vertices which are part of an edge denoting the authors of that. So there can be multiple representations. Like some might say that okay, you can arrive at another representation of these co-authorship networks which don't use hypergraphs. But yeah, at least like this is one very natural representation of co-authorship networks as hypergraphs. Okay, so Samena, uh, like right now, so that's a really good question. Like, is there a difference between first author, second author, third author? So yeah, like as we discussed previously, like there are directed graphs and undirected graphs, right? That directed graphs have like an ordering between vertices I and j. Similarly, there can be directed hypergraphs and undirected hypergraphs. where like there is specific ordering between like vertices like which are part of the edge set. Suppose like there are three vertices which are part of an hyperedge ijk, then if you impose an order on these, then it becomes a like directed hyperedge. So that is another class or like directed hypergraphs, which is sometimes like work like people work on these directed hypergraphs also. But like at least for purposes of this course or like purposes of this session, we are not going to discuss any like distinction. Like we are not distinguishing between first, second, or third author. Like we are just modeling this as like undirected network, and undirected edges are undirected. The hyper edges are undirected for us right now. Like although in real world, like if you're trying to model this network in real world, then I think like first or the second or the third author plays a very important role. Like in real world, a lot of people put more emphasis on being first author than second or third author. So in real world, maybe if you're trying to model this co-authorship network, then you'll need to model this using directed subgraphs, directed hypergraphs, because you will need to like associate these kinds of properties. But right now, let's just not get into that. Like it's more about like so okay, like someone like it's a very subjective question, like, and I don't think it's like really relevant to the course. Like, what are the weightages given to first, second, third authors? Like, like I really think it's very subjective to the area, and yeah, maybe let's not get into this. Like, let's just stick to the mathematics of it rather than like what happens actually in first, second, third authors. So yeah. So maybe we can move on to the yeah. As per maths only, so what that's what I'm saying. Like this is a very subjective thing. Like maybe like okay, like sometimes it's in some research papers, maybe like a lot of important ideas came from first author as well as second author. So they might say, oh, we want to split. Like there is no like officially like splitting of credits defined anywhere, but in some papers, like it might be that weightages for first and second author would really be important, like 50-50. Sometimes it will 60-40, sometimes it will be 90-10 or anything like. But uh, yeah, so H indices, I don't see how H index comes into the picture here. Like, okay, if you want to model and analyze like co-authorship networks, so that's what I'm saying. Like, suppose the problem given to me, so no one declares exactly like what is okay. So maybe let's just try to model these co-authorship networks. Let's just get into this problem. Okay, so suppose yeah, what I have publicly available data, there is no available data which says like first author has contributed 70% of the work, second author has contributed 20% of the work, and so on. Like no such data is available anywhere. Like no one publishes paper and says it like this. So the only available data to me is like who are first authors, who are second authors, who is the third author. And now I have a co-authorship, and I have a co-authorship network given to me now, and like where I have a set of researchers and I have a set of hyper edges. And now maybe I want to find out. Suppose I want to analyze the network and find out like who is the who is one of the most influential researchers in my field, right? So maybe influential can be in terms of who has like which researcher has the most output. So an output can be defined is in terms of like it's completely up to you how you define this metric. So if the metric is like suppose you define the metric as being like the researcher with the highest number of research papers, but suppose like if there's a researcher who has 10 research papers in which he is the like maybe third author. So but there is another researcher who had like 9 research papers, but all were first author. Then you probably want to give more weightage to like the researcher who was first in 9. Like that researcher is more influential than the one who had 10-3 like third authorship papers. So then maybe you can assign a weight by yourself. Like you can say, okay, maybe I'll weigh like first author as 60%, I'll weigh second author as 30%, and third author as 10%, or something like this. and then you can calculate like according to these weights who is the most important researcher. And then you can do like further nuances to this technique, like okay, you are defining these weightages by yourself, but like who are you to decide these weightages? So maybe what you can do is maybe you can try to learn these weightages, as in like so you can say that okay, maybe a person has a lot of papers, so maybe that person actually contributes a lot of ideas, so for that person maybe I'll give weightage more. For some other person like who has lesser papers, I'll give some lesser weightage. So things like this you can model and try to like yeah, these are all mathematical models which you can use. And yeah, that's what I'm precisely saying, like sometimes people try to learn these weights using AIML. Like they try to say okay, maybe like given a training data set, like let's try to like analyze and see the weightages for different people. Yeah, it's really, I think, Soman, it's really up to you. Like, what kind of algorithms are you using or you're not using? Uh, but yeah, like maybe like let's not get into like the kinds of algorithms which you'll be using. Like you can look it up by yourself on the internet. Like what kinds of algorithms are used to like, analyze co-authorship networks. Like we are the core purpose of this course is not to learn how to analyze co-authorship networks. It's to learn like in general like social networks, like some basic techniques and yeah, the different kinds of networks and some basic techniques. We are not going like problem specific here. Like, I think this is very problem specific and like how what network or what technique works best. But what we are focusing here on is like something more general. So let's not get into this. How do we actually do this? But I just gave you a high level idea of like what kind of techniques can one start with. But there can be further nuanced techniques, like one can start with like assigning weightages or something. But there is like this is an active research area, and maybe you have to look up to the best research papers which are available. Like as I said, like all the techniques you are mentioning, I don't know like which techniques are applied, and you can look up the research papers by yourself, like which techniques are being used these days or something. Yeah. So yeah, this can be thought of as a self-study exercise for you. Like what are we doing these days? Okay, then. So moving on, like to the eighth question, maybe. So dyadic, triadic levels occur at what level of social network analysis? So you guys might remember that like there were levels of social networks analysis which were also discussed, which were like microscopic, macroscopic, mesoscopic, and like further types like. So I hope you guys remember. So like microscopic levels are where you in analyze each vertex by itself, or like some set of small set of vertices by themselves. Mesoscopic is where you try to cluster some bigger set of vertices in themselves and then try to analyze. And macroscopic is somewhere we analyze the graph as a whole. So the dyadic, triadic levels, does anyone remember? Like what at what level do these occur in social network analysis? These dyadic, triadic levels. Would anyone like to answer in chat? Okay, so maybe you guys, I think you guys should like see the lectures like, again. Yeah, yeah. So Karpagam, yeah. So because like so, someone, why am I saying that you should probably like look at the lectures? Is because like these kinds of questions can get asked in the quizzes also, like and not in the quiz and not just in the quizzes, but in like suppose if you are doing it for like the certification, suppose you are doing this course for certification, then the end sem exam also. But yeah, like you should like remember these because these kind of things can get asked in the end exam. But yeah, although these are the definitions, but yeah, if they are asked, like you can't just say that these are definitions and just forward. You have to like answer the question. So yeah, so exactly, Karman. So that's the correct answer. That this is a microscopic view. So yeah, so this is like microscopic. So good job, sir, Karman. Uh, so good job, Karman. Like microscopic. And like maybe like this is just like this This has been discussed in the lectures also. So yeah, this is not really a super important explanation to this. This is just definition that microscopic is where you look at very small set of vertices. So dyadic is where you just look at two sets of vertices at a time, like two vertices at a time. Triadic is where you just look at three vertices at a time. So yeah, these are small sets of vertices. That's why this is microscopic analysis. Okay, and now we come to the ninth question. Okay, so ninth question says that what will be the adjacency matrix representation for the following network? So maybe we should try to like form an adjacency matrix representation for this network. So first of all, this is so we'll need to go a bit fast because I think we are running out of time. So this is like a 7x7. Like these are seven vertices in the graph, right? So these are seven vertices in the graph. So the adjacency matrix will be like of size 7x7. So maybe I'll just insert a table of size 7x7. So I'll go a bit fast, guys, because I think we should finish this. So maybe I should just shift this full to the next page for ease. Yeah. So so this will be like first row, second row, third row. So this is correspond to vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, vertex 7. So let's just see. So 1 comma 1 entry is 0 because there is no self loop at 1. But note that 1 comma 2 entry is 1 because there is an edge. Similarly, 1 comma 3 entry is 1. 1 comma 4 entry is 0 because there is no edge between 1 and 4. Similarly, 1 comma 5 entry is 0 because there is no edge between 1 and 5. 1 comma 6 entry is 0 because there is no edge between 1 and 6. 1 comma 7 entry is also 0 because no edge between 1 and 7. Similarly, for 2, there is an edge between 2 comma 1, so this entry is 1. 2 comma 2, there is no self edge, so this is 0. 2 comma 3, the entry is 1. 2 comma 4, the entry is 0. 2 comma 5, the entry is 0. 2 comma 6, the entry is again 0. 2 comma 7, the entry is again 0. Then we come to 3. So 3 comma 1, as you can see again, the entry is 1. 3 comma 2, the entry is 1. And 3 comma 3, the entry is 0. 3 comma 4, the entry is 1. 3 comma 5, entry is 1. 3 comma 6, entry is 0. 3 comma 7, entry is 1. Now looking at vertex 4. So for vertex 4, there is no edge between 4 and 1. So 4 comma 1 is 0. 4 comma 2 is also 0. 4 comma 3 is 1. 4 comma 4 is 0. 4 comma 5 is 1. 4 comma 6 is 0. 4 comma 7 is 0. Similarly, now we look at vertex 5. So with vertex 5, 5 comma 1 is 0. 5 comma 2 is 0. 5 comma 3 is 1. 5 comma 4 is 1. 5 comma 5 is again 0. 5 comma 6 is 1. 5 comma 7 is again 0. Similarly, coming to vertex 6, we see that only like 6 only has an edge to 5. So 6 comma 5 will be 1. All entries else will be 0. So this is 0, this is 0, this is 0, this is 0, this is 1, this is 0, this is 0. Similarly, for vertex 7, you can see that it only has an edge to 3. So only 7 comma 3 will be 1 and all other entries will be 0. Okay. Yeah, I just like hurried a bit through this question because I thought like we have already discussed enough about adjacency matrices, and yeah, like, you guys can verify this later on whether this is correct or not, or just try to write this adjacency matrix by yourself also. Yeah, this would be the adjacency matrix, which would. And I think like you guys got the high level idea of how to make such matrix. Just first draw an n cross n matrix and then just fill the entries easily. Just check if like I comma jth entry, like what is the I and j have any edge between them. So yeah, there is no real like magic to it, just a very small trick. Okay, so you're asking the okay, so Sai Mohit is asking that you have week 1 assignment and now week 2 as well. You want to ask whether the assignment we are doing is for practice. So yes, so exactly like Sai, the assignments which are available on like the NPTEL portal, the portal are actually quizzes which you guys have to do yourselves. Like these quizzes are marked quizzes. So if you do this course for certification, then these quizzes will be counted in your final grades. So I can't just discuss those quizzes. So, but we have these sessions where we prepare some different sets of questions, which are which are similar to the questions which are asked actually in the quiz. So, if you are able to like understand the questions which we are discussing here, you will most likely be able to answer almost all of the questions of the quiz also. But yeah, like we won't be discussing those quiz questions at all in these assignments. Yeah, these are for practice and revision, and yeah, the quizzes which will be in the NPTEL portal are actually marked quizzes, are actually graded. So yeah. Okay then. So maybe we can move on to the 10th question then. So what is a characteristic property of many real world networks in terms of node connectivity? So I think this was also discussed in the lecture. So this is also, I think, more than one option, correct? So what the problem is saying is that what is a property which is usually observed in many real world networks. So this was also kind of discussed in the lectures. So maybe I'll just discuss this by myself. So yeah, but maybe you guys should like watch the lecture and like kind of try to remember these kinds of things, because these kinds of things can definitely get asked in the business. But in general, also I think this is kind of easy to guess. Like so, in real world networks, like usually you would assume that since there is a very large population, and population usually comes from like usually in real world you usually have distributions from which a lot of things come out. So usually like the real world networks are randomly connected. Similarly, uh, they are actually scale free, where scale free means that like if you scale the networks, then uh, like the network remains the same. So uniform degree distribution is something where like almost all nodes have uniform degrees, which is not really something which you observe. And similarly, fully connectivity is also something which you probably don't observe. Like fully connected is like every node is connected to each other, which is really not true. Like just consider any friendship network, every two people are not friends of each other. So yeah, so usually what you observe in real world networks are like randomly connected and scale fields. So correct, and I don't think there's really much to it as discussed in the lectures. So uniform degree distribution means like every vertex is almost equal degree. Uniform degree means like equal degree, but this is not really true. Like there are some people, like even if you just think out social media network, there are some people who are really popular, while some people don't have any friends at all on social media. So this is not uniform, but it's still like kind of randomly connected, because there's a like if you think about a distribution, then like although a lot some people will have like very high followers, but the fraction of those people will be low, because like you can think of these as being randomly connected, because in a random distribution also like sampling a very high value has a low probability, but not a zero probability. So low probability means that the number of people who have this kind of high degrees is less. So I hope it makes sense. So here option 3 yeah, correct. So then maybe we can move on to the last question. So unipartite is a link-centric view of the network, true or false? So I think this we just like this is just a revision of what we just discussed. So this is just this question is just revision of revision. We already discussed that unipartite is a link-centric view. So yeah. So yeah. So answer is here. So yeah. So I guess this was it, which I had for uh, today at least. So we discussed like these 11 questions. So I'll post this these questions and like all of this like summary, so a PDF of everything we discussed today. Like I'll post this and like share the link with you guys. The link will be shared to you guys, I think, via NPTEL portal or somewhere. But yeah, and this lecture and this recording of this session will also be uploaded on YouTube. So one thing which I have to do is like in the second question I'll like draw an like I'll draw the egocentric view of this node after deleting this vertex 6 and like add this to this field. But yeah. So other than that, I think we are done for the day. So if you guys have any doubts, uh, please feel free to ask in chat. Maybe like we can have a couple of like, since we are already shooting over time, we can have a couple of doubts right now, and rest we can discuss in the next session. Okay, so Mohit, you're saying that you missed questions 1 to 4. So I can show you those questions, but I think I'll anyways be sharing this PDF, like the PDF of these questions to you, so you can check those questions anyways, and you can check those questions in the recordings of the session also. So I don't think you really need to uh, see them right now. Uh, and Yeah, also in case you would like my guidance, can you contact me through mails or through any other medium? So, Mohit, I think there are these on this Swayam port on this NPTEL portal itself. So there are these discussion forums where you can ask your doubts, and the TAs, like probably not me, but some other TAs which are assigned for like discussion for problem, for this discussion forum, will answer your doubts. And if you want to ask something to me specifically, you can always ask in this Teams chat, and uh, I will definitely like try to answer you the best of my capabilities. But in general, if you have any doubts, there are these discussion forums on like Teams channel, the Swayam portal where you can ask. So for my sessions, I mean, my sessions are like Monday 6 to 8 p.m. Like the timings for my session are fixed for Monday 6 to 8 p.m. I think there is another problem solving TA whose sessions I don't really know the timings. So yeah, so I think there are a couple of TAs who are taking these kinds of sessions at different times. But as for me, I'll always be taking the session. My session will always be on Mondays 6 to 8 p.m. Okay. So Karpagam, if you have like question, you can ask in chat also. Like, is it a long question? Do I need to unmute you? Thank you so much. Thanks for the kind words. Uh, Karpagam, should I unmute you? Okay, sure. Let me just. Yeah, I think you can now use your mic, Karpagam.
Hello.
Hello, Karpagam.
Hello, sir. So I just wanted to tell you, I'm attending another course of our, like, Tanmay Chakravarti sir's another NPTEL session where he,
I think your mic is not much clear, Karpagam. Uh, I'm not really able to understand. Can you try to speak a bit clear?
like, is my voice is like not audible?
Yeah, now it's a bit better, I think.
Okay, I just have to raise my voice. So I'm just attending another NPTEL course where the Tanmay Chakravarti sir, who takes the social network analysis, have share the lecture materials with the lectures. Like, if you are like, I'm not sure if you are in IIT Delhi, if you are like in IIT Delhi, like, he is actually uh, he's quite, I guess he can share he's not into all these things. He can just share the lectures because in other course, he gives the access to them. So I mean, it will not be a problem for him, I guess. It shouldn't be a problem for him to share the lectures because he is
Okay.
giving the lectures for another different things.
Okay, so you are asking me to ask Professor Tanmoy to share these the slides which he
Like,
uses to teach with you.
um,
Is it-
not to me alone, like to the entire, to all.
Yeah, maybe
Because he
I'll
should be
try asking.
comfortable sharing it because he does that for another entity. Yeah.
Okay. So maybe I like ask him and like if he's like if it works for him, then sure, like he can uh,
If you
like
like,
I'll
because
get
you are
slides.
around the campus, like if you are around the, you are actually around the campus. It looks like you are around the campus, so you can just ask him sometime whenever he's free and you are also comfortable.
Sure, like I'll try asking. Okay, so Saumen I think is saying that all he has already asked this in the Q&A to share the slides. Yeah. Yeah, like I'll also try from my end, like contacting Professor Tanmoy and ask him if,
Okay.
or maybe is maybe the slides would be available on his web page. Let me just check a bit. Oh, oh, yeah, I don't. Yeah, right now they are not available on like publicly, but yeah, I'll ask Professor Tanmoy if he's comfortable sharing it
Yes.
with you guys. Okay, so Saumen is saying in chat that uh, okay, so I think Saumen is already saying in chat that TA responded to upload soon, but so far they have not been uploaded. Like the slides from the Professor Tanmoy would be uploaded. Like I'll just maybe from my end I'll just ask again. That's the best I can do.
Okay. Thank
Okay
you.
then. Okay then. Maybe I think since we are already like quite a bit over time, I think uh, we can like if there are no more doubts, like we can close the session now. So just once again, like thanks for joining the session, guys. Thanks for everyone, and I hope to see you guys next week also. Same timings, Monday 6 to 8 p.m. So yeah, till then, like all the best for your like week one quiz. I'll just stop the recording and you guys can leave the session. Thanks for joining.